It's a great pleasure to thank all the people who've volunteered or been volunteered to give lectures in this workshop. We're all very excited and very happy to be hosting you virtually here in Montreal. And so it's a pleasure to introduce our first speaker for this morning's session, Nicolas Bergeron, this is also the first of his formal Eisenstein lectures, although it was sort of kicked off last week on Friday by a colloquium talk, which was probably attended by many of you who are here now. And so this week will be a more in-depth, of course, discussion of the topics that Nicolas covered very nicely for a general audience on Friday. So it's a great pleasure then to welcome Nicolas, who will be speaking on hyperplane arrangements and modular symbols, if I remember.
Thanks a lot for the presentation and organizing this meeting. Yeah, so today I will discuss a topological construction. In fact, it will occupy me more than today, of cocycles. So it will be the first part of two lectures concerning this topological construction of cocycles. And today I will speak about transgressing the Euler class. I will explain what it means. So let me give a small introduction to today's lecture. It will be about something that one finds in the literature. In the literature, there is a lot of things that are called Eisenstein cocycles. So, and they are not always the same. But this cocycle represents class in several type of cohomology groups. So it can be representative of class of degree n-1 of some group gamma, which is a finite index subgroup of GL and Z with scalar values, but also cocycles representing classes still of degree n-1 of gamma, but with values in some function space. I won't specify right now what kind of function space on Cn. And even more complicated things like degree n-1 cocycle of still gamma in function space that involve several type of variables, Cn times the Poincare after half plane, and maybe other type of variable that I don't want to discuss now. All these occur in the literature, and in fact I would like to add some more simple object that I will discuss at length also. Cocycle of the group GL and C, considered as a discrete group, that's the delta here, and with values in again a space of functions on C to the n. So let me just say that gamma above is a finite index subgroup. The dot here is to say finite index in GL and Z. And these cocycles are constructed by many mathematicians. So I won't name all of them, but I want to name Sczech to be sure. I should also certainly name Solomon, Nori, Stevens, Glenn Stevens, and more recently, two group of people. On one side, Charollois, Dasgupta, Greenberg, and on the other side, Beilinson, Kings, and Levin. And we will see during the week that many incarnation or related object to this cocycle, especially in the talks of Luis Garcia, Johannes Spreng. I will forget some, but also in the talk of Sharifi this afternoon, I guess. And what I want to do in my first two lectures is to explain a topological construction of that is a common source for this cocycle. So today I want to sketch a topological construction that is a common source for this cocycle. And I will start by this. I will end this introduction, let's say, by briefly said what is the general method behind this this construction. Is in fact, I already briefly mentioned this in my colloquium talk, and you can think of this lecture as a reverse engineering operation compared to the colloquium talk. I started with a very explicit map that gives a cocycle and explain that there is a topological source of this. Now I will start from topology and go to the cocycles. And the method, the topological method, is to start with the cohomology of degree 2n-1 of some space x star, where x will be either c to the n, or c mod z to the n, or c mod z plus tau z to the n. And I will erase some finite number of points. So x star will be x minus a finite number of points. And the thing is that I will lift a class to the equivariant cohomology of this space. So with G will be either, in the first case, GLNC, made discrete, or in the second case will be gamma, a finite index subgroup of GLNZ. And again, as I explained last time, a equivariant class is something like a class of cohomology omega plus the data fg plus more, so that g omega minus omega is d of fg, and fg1 g2 minus fg1 minus fg2 is d of something else, and so on. So you enrich a lot your class, and this enrichment will quickly lead us to consider a cocycle with values in the cohomology of the fiber, which will be x star. So this is what I will explain, and this will be the source of our cocycle. But of course, all this was much too fast. Now I want to start first with the basic object, the cohomology of x star. And in fact, the starting point of our construction will be Thoms and Euler class. So I will start my the first part of our lecture by discussing by a crash course on Thoms and Euler class of vector bundle, and go directly to what will be important to us for around this notion. So let me start now with the Thoms and Euler classes. So I will consider a very general setting, E over M, where M is let's say closed. You can think of M as a close connected oriented manifold of dimension D manifold. But in fact, if you're comfortable with this, you can even replace M with much more general spaces like CW complexes. The base is not very not very important. What is important is E. E is an oriented real vector bundle of rank n, which is, it will be bigger than 2. So here are the basic data, and since it's a vector bundle, you can speak of the 0 section, which I will denote by 0. And I will finally let E star to be E minus the image of the 0 section. And the first thing to know about these things is the Thoms isomorphism. Which relate the cohomology of the base with the cohomology of the fiber once you translate by n and relative to the fiber minus 0. So you have this isomorphism, which is given by the cup product with the the dual to the 0 section. So inside the fiber bundle, you have the 0 section, and you can consider the dual class to the 0 section, and it's you can take such a representative to be compactly supported, and then so it means that it's 0. It vanishes outside some neighborhood of the 0 section, and that's exactly what it means to be a cohomology class relative to E star. It means that you are 0 outside some compact neighborhood of the 0 section. So this cohomology here, let me say it like that: the cohomology of E relative to E star is the same as the cohomology of E represented by compactly supported forms in fibers. Okay, and so a particular class in here is the Thoms class. If we let U which is dual to the 0 section compactly. So if you want to think in terms of differential form, it's like a closed form on the total space, which is compactly supported in the fiber and has integral 1 on these fibers. So this is dual to the 0 section, and this is called the Thoms form, and it's also the image of 1 in through the Thoms isomorphism. So 1, the generator of H0 of M. And this is called the Thoms class. And this will be the basic class that we will consider. In fact, we will soon consider cases where this Thoms class can be transgressed, meaning that you can find a pre-image in the long exact sequence of the pair. So consider the long exact sequence of the pair E star. So let me write it. So here, and you have the connecting. And I stop here. So the Thoms class U belongs to Hn of E relative to E star, the degree n cohomology of E is isomorphic through the zero section with the degree n cohomology of M. And in fact, so I should have put U here. And through this map, U is mapped to a class here, which is called the Euler class. So you consider the Tom class, you map it to En of the cohomology of E, and you pull back by the zero section. And what you get here is called the Euler class. And what will be important for us, let me write it like this, a corollary, if the Euler class is 0, then the Tom class U can be lifted in the cohomology of degree n-1 of E star. And that will be really the basic ingredient in our construction. So let me say a few words on this on the meaning of this Euler class. The Euler class, let's write it again, is equal to the pullback by the zero section of the Tom class. And the Tom class is dual to the zero section. So you pull back the zero section by the zero section. So you are computing the self-intersection of the zero section. So it's dual to self-intersection of the zero section. So you have the zero section from M to E. You pull back the zero section, and you look at the zero section, and you modify it a bit to make it transverse to itself, and you see you have a class of degree n, which is the codimension, and this is the Euler class. And now, if it vanishes, it means that there is you can consider a secondary invariant. And the secondary invariant means somehow how you link with the zero section. What is the linking number with the zero section? So in some sense, if you can lift U to a class in Hn-1 E star, what you are considering, you find a way to give a meaning to linking with the zero section. It's not canonical because there is a kernel, which is the degree n-1 cohomology of E. But each time you find a lift, then you choose a way to measure the linking. Of course, it would be much better to have a canonical way to find to measure this linking, and we will come back to this later. But at this point, what I want to say is that, okay, the Euler class has some interesting topological meaning, but in many situations, it can be proved to be 0. Then you get a new class, the lift of the Tom class, which is in degree n-1. And I want to convince you that there will be a rich arithmetical meaning of this class. But to do so, I have to consider cases where the Euler class can be 0. And there are two natural situations where the Euler class is 0, and that will be the situation we will discuss. So let me say it like that. There are two natural situations where the Euler class is 0. The first situation, the simplest one, is comes from the following remark. If E is not only a real vector bundle, but admits a structure of complex vector bundle, of complex vector bundle, then if E is flat, the Euler class, which identifies, because E is a complex vector bundle with a top chain class, has to be 0 because of the flatness. Okay? So be careful, because sometimes it's a common mistake that the Euler class is a characteristic class that is not 0 in general, even if the that can be non-zero even if the bundle is flat. But if the bundle is complex, as a complex vector bundle structure, then flatness implies vanishing of the Chern class, of course, and the top Chern class is the same as the Euler class, so the Euler class vanishes. So this will be a first situation where the Euler class is 0, and I would say that it is a non-arithmetic case. Here it will happen in some non-arithmetic situation, but already you see it's quite interesting. And now there is a more arithmetic case where the Euler class vanishes. Is this second case? If E is a fiber bundle with structural group contains in SL and Z, which is equivalent, maybe it's better to think of it like that, it's equivalent to the fact that there exists a sub-bundle, which is a sub-bundle whose all fibers are lattices in the vector bundle. So it's a sub-bundle whose fibers are lattices in E, so isomorphic in particular to ZF. So this is the same as having a structural group SL and Z. And in that case, there is a very nice theorem, an elementary theorem of Sullivan, which says that then the Euler class is 0, not in integral cohomology, but in rational cohomology. So this is another situation where the Euler class is 0, and we will be interested in both this situation. And since the Sullivan theorem is it will be quite important for us, I will give a proof of Sullivan theorem, insisting on the part that will be really crucial for us. Okay, so that will be my next part. I will now give a proof of Sullivan's theorem.
Could I ask first? Is the vanishing in part 1 for integral cohomology or just rational cohomology?
No, rational cohomology. Mm.
Thank you.
And yeah, I should. Yeah. So let me now give the proof. You can compute the Chern the Chern class using the connection, and then using the flat connection, and since it is flat, it has no curvature, and so the cohomology class is 0. So you use the RAM representative to prove this. It will reappear later in the lectures. Yeah. Okay. So let me give a proof of Sullivan's theorem. So again, we are in the following situation. We have this sub-bundle that consists of lattices, and this yields this yields a group bundle. Namely, you take the quotient E by EZ, and the bundle is a bundle whose fibers now are tori. And inside this group bundle, I will consider some particular points. I will denote T of M, the set of M torsion points in T. And what will be crucial in the proof of Sullivan's theorem, as it in, and will be, and in fact, this is the part that will be crucial for us too, is the following lemma. That says that suppose you have taken M strictly bigger than 1, then the class, the cohomology class of the set of M torsion points minus M to the N, the 0 section. This represents a class in cohomology. And I will consider the rational cohomology, and in rational cohomology, this class is 0. And this theorem is very easy. But before proving it, just note that because it's 0 in cohomology, it means that you can lift this to a class of degree n-1 in T minus Tm. So let me just make this remark. So you can lift to a class of degree n-1 by the long exact sequence we considered just before in T minus Tm. So if you want, this class is the linking number around the M torsion point. And now if you pull back by some torsion section that is prime to M, you get a class of degree n-1 on the base. So this gives a machinery to produce cohomology classes as long as you have a tori bundle over some base. And for example, you can play with, you can take for, as the base M the moduli spaces of lattices with a quadratic form. So I mean, you can take the arithmetic space associated to a congruent subgroup of SL and Z, and in that way you produce cohomology, interesting cohomology classes. So that's why it can be interesting to us and related to these Eisenstein classes. But now let me give the proof of Sullivan's lemma. And the proof, in the proof, again, the only thing you consider are the fibers, and we'll consider the multiplication map by M. So the map, the multiplication by M map induces, so you multiply in the fiber, which induces a map from T to T, which is a degree n to the n covering. So it's a covering map of finite degree. And now, as such, if you consider the direct image map and the pullback map, so let me say the direct image map in cohomology, and the pullback map in the cohomology, since M is a covering map of finite degree, they satisfy that the direct image map composed with a direct image map is equal to m to the n, the degree of the covering, times the identity on the cohomology. So this is a crucial observation that only depends on the fact that the map is a covering map of finite degree. And so in particular, the direct image map is injective on rational cohomology. And this is how we will prove the vanishing of the class, because now consider the class of the M torsion point. This is the same as the pullback by M of the class of the zero section. The set of points that are M torsion are exactly the ones that are mapped to zero by M. Now the direct image of the zero section is, of course, the zero section itself. So if you take the direct image of the M torsion point minus M to the n, the zero section, what you get, here you have direct image of the pullback of the zero section. And since direct image, since pullback composed with direct image is m to the n times the identity, here we get m to the n times the zero section minus, again, m to the n times the zero section. And so we get 0. But since the map is injective in rational cohomology, of course, the class has to be 0 itself in rational cohomology. And this proves the lemma. So as I said, this will be really the crucial point in the construction. But nevertheless, I want to finish the proof of Sullivan's lemma, Sullivan's theorem from that. So it won't be used later, but let me say it anyway. And to finish the proof, instead of looking first at the bundle E, I will look at a bundle that is isomorphic to E, which is the normal bundle of the zero section inside the torus. So I will note the following corollary. The Euler class of the normal bundle the normal bundle of 0 in T vanishes. And how do we prove that? Let me say it in a few words. You can consider the cohomology of degree n of T relative to T minus the zero section. So here you have the Tom class, and you consider the map, the restriction map to the cohomology of T, and this map to the zero section. And now remark that m times 0 is equal to 0. So if you compose the pullback map by m and take the zero section, then you have the same map that the pullback by 0. So if you pull back the M torsion point by the zero section, it's the same since the M torsion point are the pullback by M of zero, it's the same as the pullback of the class of the zero section. And this, and this is the Euler class. So it's, you can see the Euler class both as the pullback of the zero section by 0, or as a pullback of all M torsion point by 0. But now, remember what we have proved. We have proved that this is 0. And we have proved this. So what we have is that 1 minus m to the n times the pullback by 0 of the zero section, okay, we pull is equal to 0 in the cohomology of M. And since M is bigger than 1, this is non-zero. So this class, which is the Euler class, has to be 0 in rational cohomology. Okay? So the Euler class of the normal bundle is 0. And now, how do we conclude the proof of Sullivan's theorem? It's just that the normal bundle of 0 inside T is isomorphic to the bundle E. So so it has a 0 Euler class. So again, the crucial thing was Sullivan's lemma and the fact that the multiplication by M map is a covering. If you don't like the end of the proof, don't worry, it won't be used later. But the crucial thing is a small lemma. Okay, so that will be we'll see this coming back several times, and now I want to go back to the mainstream of my talk, namely the construction of cocycle, and explain where the cocycle will come from. So this will be the topological construction of cocycles. And when I say first part, is that I will discuss first the affine case. So again, let me say that there are two cases. Let me repeat that there are two cases where the Euler class can be shown to vanish. The first cases is if we have a flat complex vector bundle, and the other cases is the case where we have a bundle with a structural group contained in SL and Z. So we will consider both cases, and in fact we will consider universal bundles associated to these two situations, either GL and C discrete. So here this will be the case of flat complex vector bundle, or gamma, which is the finite index subgroup of GL and Z. We will consider both this situation, and in both this situation, we will be able to lift the Tom class because of the vanishing of the Euler class. And here I start with the simplest case, which is the affine case. And so the fact I want to explain is the following. If consider the fundamental class of Cn minus 0. So Cn minus 0 is homotopy equivalent to a 2n minus 1 sphere. So there is a cohomology class in 2n minus 1 Cn minus 0, of Cn minus 0. And this class admits I will discuss later this preferred, but first I will discuss that it admits a lift in the equivariant cohomology of Cn minus 0. So after we have what we have seen up to now, it will be quite short to prove this, but the longest part will be to explain the different words in that statement. And the first thing to explain is what is equivariant cohomology. I've tried to give an intuitive meaning of it, but now it's time to give a precise formulation for what is equivariant cohomology. So first, I haven't said it, that here G again is GL and C considered as a discrete topological group. And so what will be the definition of equivariant cohomology of, so here we are considering Cn minus 0, but one could consider any topological space with an action of G. And equivariant cohomology can be defined by, and it's called Borel construction of equivariant cohomology, as the cohomology of a big space, namely EG cross G. So I will define all this, Cn minus 0. So what is this? It's a universal bundle over the classifying space BG of my group G. So BG is in fact EG mod G, where EG is a contractible topological space. In fact, it will be a simplicial set, but such that G acts on EG freely and properly. So this BG, now the quotient of EG by G, is a classifying space. For G, so in particular, the cohomology of BG is the same as the group cohomology of G. So now the standard way to construct such a classifying space is to consider the geometric realization of a simplicial set, and that's the so. I won't need much about all this, but I just want to say it briefly. EG will be a simplicial, and the simplicial set whose in degree k, this is the k plus 1 folded k plus 1 product of G, and you have some face and degeneracy maps. So the usual one, the E boundary of of G0, Gk is just forgetting about the ith element here. And the degeneracy map goes from G0, Gk, and you map it as G0, you double Gi, and Gk. So you should think of it as a big simplicial space, infinite dimensional, and it's a bit more than that because it's directed. The corresponding multigraph is directed. Okay, so it's and now if you and now there is a simplicial. You can have a geometric realization of this space by putting simplices each time you have G0 Gk. You glue simplices according to this phase and degeneracy map. So in some sense, that's that's what you do with a finitely generated group, but in fact you don't need you can do it in with any group, even such a big group as the GLNC discretized. And so once you have it, you have this big space which is contractible and on which G acts. So G acts on EG by, so you have two choices. I will use this this choice here. And the quotient EG mod G is now a classifying space for G. So that's our big base space, and that's why I insisted in the beginning to say that we don't really care about how is the base space. We can take very weird space, and now from this we can build a bundle, and the bundle is, as I said above, is EG cross G mod. Let's say first CN, the CN bundle. So this is just the product EG cross CN, and you take the equivalence relation that x G minus 1 GV is equal to, is equivalent to XV, where X belongs to EG and V to Cn and G in G. Okay, so once you have a k-tuple of elements, you may translate them by the right action of G, and if at the same time you translate G by the left action. So that's the equivalence relation. And now, of course, EG. Map to BG, EG mod out by G. You just forget the fiber variable. And this is a CN vector bundle that is flat. So you have a universal bundle over the classifying space of G. And so now that we have that, formally we can do exactly what we have done before. We have a Tom class, except that we have to remember that we are in degree 2n. The Tom class, it's an element in the degree 2n cohomology of this bundle. So it's a G equivalent class of Cn relative to Cn minus 0. And we still have, and we have the same long exact sequence. That writes now like that. And here, and the Tom class is here, and it maps to the Euler class here, which is just the Chern class, the top Chern class, degree 2n, of Cn, and because it's flat, then it's 0 because of flatness. So U has a lift, and this is exactly so I haven't discussed yet the preferred, so I will postpone this for later discussion. So I will come back to this construction from another perspective, from a differential form perspective, and get a preferred lift. But at least for the moment, we know that there is one lift that I will call S affine. So S is for such because he constructed many cocycles that are related to that. And affine is affine. And so we have a equivariant class here. And this is the lift that was referred to in the fact. So again, what we have done here, we have considered the general, oh, I see that. Sorry, I haven't turned off my conversation things. Okay, so maybe we can discuss later the question. Sorry, I haven't, I didn't notice the question before. So let me say what we have done so far. So we had the universal bundle, the Cn universal bundle associated to the group G. Okay, so because it's a flat bundle, the Tom class, it's a flat complex vector bundle. The Tom class can be lifted to the degree before. So you have a degree 2n-1 class of the universal bundle Cn minus 0. And this Cn-0 is precisely what lifts the class of the fundamental class of Cn. Here, I should say that there are maps here where you forget about the G. So anyway. So that's the starting point of the construction, this equivariant class. And now I will finish today by explaining how we go from that to a cocycle. So now, and in fact, this will come from a very general remark. Is that if, so general remark, if suppose X over C is an affine n-dimensional variety with an action of G on this variety. Now, again, we can consider the fibration EG cross GX over BG. So now it's a bundle with fiber X. So it's a fiber bundle with fiber X, and we can consider the spectral sequence associated to this fibration. So this fibration, there is a base, which is the classifying space for G, and the fibers that are all X. So the associated spectral sequence is cohomology of the base, so cohomology of G, with values in the cohomology of the fiber Q of X and this converges to the cohomology of the total space in degree p plus q. But the cohomology of the total space, by definition, is the equivariant cohomology of X. So here is the equivariant cohomology is what we want what we want to compute, and this is a more standard cohomology group of G with respect to the cohomology of the fiber. But now, if X is affine, since we have assumed that X is affine, the cohomology of the fiber is 0 in degree bigger than its that's the complex dimension. So it's 0 in degree bigger than n. So we get a map that goes from the equivariant cohomology, let's say in degree 2n minus 1 of X, to the cohomology of degree n minus 1 of G, with to the first degree where there is cohomology in the fiber, namely Hn of X. Before that, there is no cohomology, so you get nothing. So there is a map here. And that's how we construct the cocycle. Except that at this point, you could say, okay, but you will apply this with X equal Cn minus 0, and Cn minus 0 is not affine. So I cannot do that. I cannot do that. So what can I do? I can force it to be affine by just restricting our class to a smaller variety, which will be affine. So what we do, we may restrict our class f affine to an affine open subset U inside Cn minus 0. But remember, we have to do this equivariantly. So we want this open affine subset to be G invariant. So one will need U to be G invariant. That's too much to ask. So one way to restrict to an open subset that is affine is to erase, let's say, an hyperplane. You get then an affine variety. But if you want that it is G invariant, you want to erase all translate of this hyperplane, and that makes a lot of hyperplanes to erase. So it's a bit strange. But one can formally take U to be Cn minus all the hyperplanes. This seems to be a lot, but this can be done if you consider, for example, a direct limit of hyperplanes. So that's, we cannot do that, but what we can do to make this precise, you can start by giving yourself L, let's say, a finite set of linear forms, and let UL be Cn minus all the hyperplanes associated to this finite set. And now what your class gives is a class in the cohomology of degree n minus 1, sorry, of G with respect to the limit of Hn of UL. And this limit now is really J invariant. So everything can be done. So that will be one goal of the next lecture, is to make this rigorous. But to conclude, I will say that now, finally, the marvelous theorem of Bergeron tells you that this cohomology group is zero. Oh, sorry. No. The cohomology of an affine, an hyperplane complement in Cn, like QL, is 0 in degree bigger than n because it's affine, and is given by the meromorphic forms of type obtained as product of dl over L. So let me just say that this. Yeah, sorry. This is equal to what I will call the meromorphic form on Cn from generated by dl1 over L1 wedge dln over Ln with Lg linear form. So S affine yields a more interesting class, which belongs in the cohomology of G and takes values in the degree n meromorphic forms on C to the n. And this will be the cocycle I will discuss later. And I want to stress that this is really a marvelous theorem of Bergeron, because this is what enables you to go from the topology to something which now sees really the meromorphic structure on the fiber. And so you have a cocycle, starting from a purely topological construction, you end up with a cocycle of G with values in algebraic object, namely the meromorphic form on C to the n. And my goal now tomorrow will be to first make this construction more rigorous, then to explain what happens when you replace GL and C by gamma, and what type of cocycles you get, and in the later lecture to compute. I mean, for the moment we have a cocycle, an abstract thing, and we want to compute and give formula for this thing. So this will be the goal. So if I went too fast today, I will say almost all this stuff several times during the week. So hopefully this will be okay. That's where I stop. Thanks.
So thank you very much, Nicolas, for this lecture. Are there any questions or comments?
Yes, may I ask? I have a few comments.
Actually, can I ask people who are asking questions? I think it would be nice if you could, if it's possible technically, to open your cameras. So we can see you.
Sure. I wasn't camera ready, but
I mean, unless you're have internet problems or something, but I think it's a good form. People can.
Okay. So there's a couple of comments. The first one is about these two cases that you gave where the Tom class vanishes. And the first case was where you were looking at a complex, flat complex vector bundle. on M. And the comment is that so the existence of such a bundle is very intimately related to topology of M. Mainly, there's a theorem that this bundle comes from a representation of pi1m into GLNC, where n is the rank of the bundle.
Yeah.
And there's a theorem of well, there's a special case of such bundles called stable bundles, which correspond to representations of pi1 into the unitary group. So it's an old, I mean, in the case of curves, it was a theorem of Narasimhan and Sheshadri that every unitary representation gives you a stable bundle. And it was generalized to higher dimensional Kähler manifolds by, I think it's called the Hitchin-Kobayashi correspondence. So in your case, will unitary representations play, well, first of all, will this viewpoint play any role that they're coming from representations?
No, in our case, you'll see that there are really non-unitary representation. I mean, the thing is precisely that. So first, I applied this. You see, in the case where the representation, if you want, is the image is the whole GLNC. When I apply this at the end, the group is GLNC discrete, and the image, of course, is the full GLNC. So it's a universal bundle. So it's far from being unitary, as far as you may hope. And in general, that will be the situation. I mean, we are considering linear group representation that won't be unitary.
Okay, so that's actually great, because then this theorem of Narasimhan and Sheshadri was generalized by Hitchin that so the representations, so representations into GLN, which are not necessarily unitary, they correspond to what are called the Higgs bundles, not just stable bundles. So it would be interesting to see what Higgs bundles one gets. The second comment is, so for the second case, you said if one has lattice bundles over M, then this property is also satisfied. So the question is, you always have a lattice structure in a vector bundle, which is coming from a variation of a Hodge structure. And well, again, I guess if you're, this will become important if you're looking at moduli, if you're looking at Shimura varieties, let's say. Because they would give you variation of Hodge structures. I was just wondering if you know the other way around. If one has a lattice bundle, is it always coming from some variation of Hodge structure?
No. For example, no, I mean.
I actually think there's a conjecture in this along these lines of Simpson.
Okay, so maybe I'm not okay. I need to no. I mean, it's not my main. So I'm not confident enough to answer properly the question. So I prefer not to say something wrong. But
especially since you're being recorded.
Huh?
Being recorded.
Oh. I'm sure I've been recorded saying something wrong several times already, but let me not add.
And the third comment is rather trivial. It's so in this Briscoe theme, is there an action of permutation group on these meromorphic forms?
Of the permutation group?
Yeah.
Yes, I mean the form I consider is wedge product of. So I'm not sure.
So let me.
It's a wedge product, so it's anti-symmetric.
Actually, okay, not just the permutation group, but the braid group. So I know in the case of Cn minus hyperplanes, the one which was considered by Arnold, there this cohomology has an action of the braid group, the full braid group. But since these, I mean, that hyperplane arrangement is very simple. So since over here there's a more sophisticated hyperplane arrangement, it might not be the full braid group, but some subgroup or something like that.
No, here it's the you take all the hyperplanes. So Okay, I don't know what exactly what so you expect, but yeah, I'll try to. Okay, we can discuss this tomorrow when after I will have described this in more detail, this construction.
Okay, thank you.
Thank you.
So I think that unfortunately now the schedule this morning is a bit tight because we have 3 speakers, and we're starting with Paul Gunnels in a minute. I should say that there'll be a time, of course, I think tomorrow there's a bit more room in the schedule. So there's a 30-minute break after Nicolas' lecture tomorrow morning. So if ever people had other questions that or things they wanted to ask, then there'll be plenty of opportunity in the course of the week. So yeah, so I want to just now close thanking Nicolas again for his lecture.
Thank you.